Hi, I'm Yue Wu from Oxford and Alan Turing Institute. Today, I would like to introduce the concept of random periodic solution and consider its numerical approximation via the backward Euler-Maruyama method. First, I would like to give you a brief idea of what it is. The random periodic solution. A random periodic solution is based on random dynamic system. For this, we will indicate a separable Banach space for the semi-flow U to live in. A semi-flow U will satisfy the flow property. A map Y is said to be a random periodic path of periodic tau for the semi-flow U if it is satisfied two conditions. The first condition is quite similar like the flow property. If you starting the random dynamic system from any time point, from any initial point Y, then after any time, you will still stay on the same trajectory. The second one is about random periodic property. After one period, the value of Y at time S plus tau is equal to the value of Y at time S, but with the realization shifted by theta tau. Let's compare it with the well-known concept of the deterministic periodic path or the stationary path. If the path is not random, so we don't have omega here, then it degenerates to the deterministic periodic path, right? And if the random periodic property is true for every positive tau, then the definition will reduce to a stationary path. There's some literature to deal with the existence of random periodic solution for different cases, like for co-cycles, semi-flows. So we have a theoretical, footing for random periodic solution. And in general, the random periodic solution cannot be solved explicitly. So we consider a numerical experiment. Here, the numerical approximation is of infinite time horizon. So it will cause some problem. There are some previous attempts for the stationary solution and for random periodic solution, but the only literature existing for the random periodic solution is this one by Feng, Liu, and Zhao. They studied the Milstein method and forward Euler-Maruyama method for the random periodic solution of a dissipative SD under the Lipschitz condition. Because they consider dissipative SDE, so they can make use of pullback to study the system in the long run. In my paper, I studied the backward Euler-Maruyama method for random periodic solution of a dissipative SD under the one-sided Lipschitz condition. And I will show the existence of the random periodic solution to such numerical scheme. To set up the problem, we first construct a two-sided Brown motion and consider the following SDE. You can see I separate the drift term into two. One is linear, one is nonlinear. And for the linear operator A, I will assume it is positive definite with all the eigenvalue being bigger than 0. And the smallest one will be denoted as λ1. And for the nonlinear part, F and G, they will be periodic in time with period tau. And in addition, we assume F is one-sided Lipschitz condition with a coefficient CF. And G is said to be periodic and continuous, so it is bounded by sigma. Then under assumption A to 1 to 2, we know there is a unique solution for the targeted SD, and we can write down the form using the variance of constant formula. To study the random periodic solution, we also need to assume there exists a standard P preserving ergodic Wiener shift theta such that this equality holds. Then we consider the path from time minus k tau. We will show when k tends to infinity, there exists a limiting path x star in L2 space. And this limiting path is a random periodic solution to the original SDE. And you can write it down like this. To achieve this, we need 3 further assumptions. The first one is the coefficient for F is smaller than the smallest eigenvalue of A. So this condition ensures the solution can be dominated by the linear operator. We also assume the initial condition is bounded in L2 sense. The last assumption is borrowed from Suzhou and Suzi's paper. So we assume the boundedness for F in the tangent direction. So this ensures the existence of a global semiflow for the SDE. Then under assumption 1 to 5, we are able to show there exists a unique random periodic solution such that it is the limit of the x minus k tau, regardless of where it starts. To show the existence, we need some extra lemma. First, we need to show the boundedness of x minus k tau in L2 sense. Then we need to show the dependence on initial conditions. So we measure the difference of two paths, and we will show the difference is give you a contraction map. Then with the help of assumption 5, which tells you there is a global semiflow, we can show there is a limit in L2 such that you just send k to infinity to make such limit. And to satisfy the first condition in the definition of random periodic solution, we just need to make use of global semiflow again. Because x minus k tau satisfies the global semiflow property, then we send the lim k to infinity. Then the limiting path also satisfy some property, right? The second one is the random periodic property. We need to show the limiting one. The limiting path satisfy random periodic property. To achieve this, we only need to show the s minus k tau satisfy random periodic property. Then we're sending k to infinity to get the results. Yeah. Now let's move to the backward Euler-Maruyama method. To formulate the scheme, we first give an equidistant distance partition on the time horizon R with step size h. We simulate the path starting from minus k tau. And the scheme is given by recursion and can be implemented on iteration. We have further prediction on the drift term only. The well-posedness can be ensured by applying the uniform monotone theorem. The second main result today is under assumption 1 to 4, and for any h with some conditions, then the backward Euler-Maruyama method we propose here admits a unique random periodic solution on the time grid, right? So the proof is more or less the same, and we make use of the trick to deal with one-side ellipses, but I will skip it due to limited time. And then we look at the convergence. For this, we need extra assumption which characterize the continuity of f in spatial variable. Then on the assumption 1 to 4, we can show the backward Euler-Maruyama method converge to the true solution starting from minus k tau with order half. In addition, if we assume assumption 5, we can show the random periodic path from the backward Euler-Maruyama scheme converge to the random periodic path to the target SD with order half. Compared to the explicit method given by Feng, Liu, and Zhao, the backward Euler-Maruyama method didn't specify too much condition on the step size. Each can be as large as 1. So we can expect, a convergence even when the step size is large. Next, I will show you a numerical experiment. We have a very simple example, a one-dimensional SDE with period 1. It is easy to check the example satisfies assumptions. First, let me show the periodic path. Yeah, maybe let's skip this. The second thing we can demonstrate is periodic. periodicity. There are two ways to show it. The first approach is simply checking the limiting path t of a realization omega equals to the limiting path at t+1 with the realization shifted by theta -1. And we can choose the approximation as a pullback -30, and we choose t to be -4 to -1. Then from the plot, you can see we have two segmented process, which are identical, but with a time lag one. This time lag is our period. Another approach to show periodicity is to verify the limiting path at time t with realization shifted by theta -t is a period with periodic tau. To achieve this, we write down the SDE with realization shifted by -t, and we starting from t0, and we simulate the path until we reach time t. Therefore, for each fixed t, we got one evaluation. Then we concatenate them together to make a new path, and we draw the plots here. Yeah, and the final example is we compare backward and forward, and you can see when the step size is large, the backward will give you a smaller arrow, and when the step size is small, they will give you more or less the same arrow. So which means when the step size is large, the backward Euler-Marry method will give you the advantage of a quick or early convergence. Thank you.